Okay, hello everyone. Thank you for joining us today as we connect with Research Vessel Falkor and talk with scientists studying submarine volcanoes in the Pacific Ocean near the nation of Tonga. My name is Logan Mock-Bunning, and I'm on the communications team for Schmidt Ocean Institute. A big thank you to Exploring by the Seat of Your Pants for gathering us all together. We love participation from all of you watching, so please ask questions. You can ask questions on the YouTube chat bar on the right of your screen, or send us tweets with the handle Schmidt Ocean or hashtag #UnderwaterFire. Please go ahead and post questions now or at any point in the Hangout. We'll be answering questions for a few spots in the presentation, and we've also set aside time at the end for additional Q&A. To get things rolling, a bit of background. The Schmidt Ocean Institute was established in 2009 with the goal of advancing frontiers of ocean research and exploration through technological innovation, operational support, and open sharing of information. Our research vessel Falkor is equipped with cutting-edge technology, including multi-beam sonar and high-performance computing systems. Right now, Falkor has on board a multidisciplinary team, including experts in geology, biology, and chemistry. The leader of this team is Dr. Ken Rubin from the University of Hawaii, Manila. Thank you for your time, Ken. Would you like to take it from here?
Thank you, Logan. I'm standing here with Bill Chadwick.
Hi, Bill.
Hello. And yeah, we're working together here with our team of scientists at some submarine volcanoes in the Kingdom of Tonga. And we're going to give you a little presentation about what we're working on and what we're doing here. And then we hope to get lots of questions and we'll provide some answers to you. Monica? Yeah, we're going to show you guys a little show first. Woo. Yeah, so this is the, oh, we're sharing our screen. And if you see us moving around, it's because the ship is moving and we're trying to stay balanced. Yeah. So this is the name of our expedition. Yeah, can you guys see this? Do we know that they can see that? Oh, well, we're going to assume that you can see it.
We can see it.
All right, thank you. That's a picture of a submarine eruption that we witnessed in this same place about 7 years ago.
What channel?
This channel, but don't watch the live stuff.
Here, can you do it on the?
Go to the next. Let's just go to the next picture. That's the ship that we're on, the Falkor. And the only thing that's different about that ship from the picture you see is now they painted it blue. And I like it better blue. I didn't like the green, but we're somewhere inside. The next slide. And this is where we are right now in the ocean. So we're where the star is. We're right here in the country of Tonga. That's New Zealand. Oh, right. You can't see me pointing. Duh. Sorry. So one thing you might be able to tell in the upper right-hand corner of the picture is you can see the very tip of Baja California. That's just south of California in the United States. And the star is where we are, down south of the equator. We're in the southern hemisphere. It's very hot and it's tropical here. And we're in the middle of Polynesia. Yeah, so here's some stuff that we're doing that we're hoping to learn on this expedition. It's all about submarine volcanoes. We want to know how they grow. How fast do they grow? How do they change? How often do they erupt? What are the style of eruption? And some of you may know, maybe all of you know, that submarine volcanoes have hot springs at them. And those hot springs are where hot water with different kinds of chemicals in them come out of the seafloor. There's unusual organisms living at them. And so we want to study those things as well.
The thing that brings us to this part of the world, which is kind of remote, is that this area happens to have probably the densest concentration of submarine volcanoes anywhere on Earth. So that's why we've come this far to study this this area. So this slide shows some of the technology we're using on this expedition. This is showing various kinds of autonomous underwater vehicles, or AUVs. The autonomous word basically means that the vehicle is not connected to the ship when we put it over the side. It goes down. It's battery powered. It has computers on board, so it's pre-programmed on what to do, and it navigates itself. So it's a pretty sophisticated robotic vehicle. That picture on the left shows different kinds of AUVs. There's lots of different shapes and sizes. And the picture on the right shows the Sentry AUV. That's the one we're using on this expedition. Okay. And the other main tool we're using right now is called a CTD, which stands for Conductivity, Temperature, and Depth. It's basically a package of instruments that we lower over the side of the ship on a cable. And it's got lots of different sensors on it. It's got bottles that can collect samples of the seawater. And we're basically using it to look for plumes of hot water that are coming out of the seafloor from these seafloor hot springs that Ken talked about. And so there's, we can look for higher temperature or cloudier water or different chemical signals, and that all those things indicate that there's this hot spring water coming out of the seafloor and drifting around above the bottom. So we're looking for those because we're interested in where the vents are on the bottom. So, and we've got two different parts to this expedition. The first part is now with the CTD and AUV, and the second part will start right after Thanksgiving with something called an ROV, or remotely operated vehicle. So the big difference between an AUV and an ROV is that the ROV is connected to the ship by a cable. So that's a picture of the one we'll be using on the left there. That's called this ROV Sebastian. That's its name. And it goes down on a cable. We can control it from a control room on the ship. So there's pilots in there, and the ROV has two manipulator arms. It's got video cameras and lights and other kinds of sensors. So we can go down to the seafloor and look around. We can drive it around and collect samples or deploy instruments. And the picture on the right is a picture of what the control room looks like on the ship here. So we'll be doing all that after Thanksgiving. Let's see, this is a map of the area we're working in. You can see, so the colors on the map are different depths. So the purples and blues are the deepest parts, and the yellows and reds are the shallowest part. So you can see in the bottom, in that box that's surrounded by orange, the orange square or rectangle, there's two red dots. Those are two different volcanoes. The one on the left is the one we're most interested in because that's the one that has been the most active. It's erupted, we know it's erupted like 7 times in the last decade, last 10 years. A couple of them have just been in the last year and a half, we found out. And so we're going to be visiting those eruption sites with the AUV and the ROV. And then there's a whole string of, in the white box, there's a whole string of other nearby volcanoes, all those yellow dots. Those are mountains on the seafloor, basically, and those are all active volcanoes also. And at where there's seafloor hot springs, there's all kinds of strange and wonderful animals that live at them and get their energy from the chemicals coming out in the hot springs, which is kind of amazing. So there's, in the upper left there, you can see a seafloor hot spring that's called a black smoker. You can see that black smoky looking stuff coming out of the vent. Upper right are a bunch of snails and crabs at one vent. Lower right are some barnacles, hydrothermal barnacles, and the lower left are some mussels and a fish. So different vents will have different animals living at them. And they're all species that live nowhere else on Earth. A lot of them, they only live at these deep sea hot springs, and that, you know, you don't find them like in lakes or anywhere on land, because they're specifically adapted to living at these deep seafloor hot springs. This is a closer view of that one seamount that we're particularly interested in, called West Mata, the one that we've seen erupting and has erupted 7 times in the last 10 years. So we're looking at those eruption sites. We're mapping them out in as much detail as we can and getting ready to dive on them with the ROV in a couple weeks. And this is one of the sites where we figured out that this volcano had erupted in the last year and a half. So what we did was we came out here and did a survey of the seafloor with the ship's sonar, and we could compare that survey to one a couple of years ago, and then we can look for changes in the 2 surveys. And those areas in color are places that change depth by a lot, and that's where an eruption had happened and lava had piled up, and so we can see that change in the seafloor by comparing those 2 surveys. And this is, again, a picture that was taken in 2009, so 8 years ago, when the last time we were here with another ROV when it was actively erupting. So we don't know if we're going to see that when we make our ROV dives in a couple weeks, but all of us are secretly hoping so.
So this is more pictures from 2009, and what the last picture and this one were supposed to show you are some of the different ways that the volcano can erupt. That previous picture was the volcano spitting out little pieces of molten rock, which is an explosive form of volcanism, and those rocks pile up around the volcanic vent and make a cone-shaped feature. What you're looking at here are lava flows of different types, and these flow across the seabed, and they tend to make different shapes. The volcanoes grow by a combination of these 2 different kinds of eruption styles, and we're really interested in studying not only during eruptions, but how the long-term history of eruptions at a volcano affects the shape of the volcano and all the properties that it has, such as the locations where it can host hydrothermal systems, the hot springs, and where the organisms live, and how the volcanoes might change over time. Oh, and I think this is the last picture. This is a picture of us taking a sample of a type of a lava flow. It's called a pillow lava. It's not something you'd want to sleep on. It's not soft, but it's shaped like a pillow. And you can see that bright orange stripe. That's a place where, even though this is a still picture, when we were watching it in video, that lava flow was stretching and growing. That's how they lengthen. And the pilots of the ROV stuck the metal bar into that bright orange part and pulled out a rock. And we still have that rock. It's the first molten lava collected in the deep ocean. And it's very, very useful for us to study these sorts of rocks because they're very pristine. When a rock sits on the seafloor for a year or a decade or 100 years, the longer it sits there, the more it changes. And we want to see what the rock looks like right when it erupts. And so this is the way to do it. And that's a picture of that rock. So I think this is the last picture. And you can see the little hole in that rock. That's where the pole went through it. And there's just a hammer in my hand showing you basically the size of that rock. And it's a very precious rock. And we enjoy working on it very much. So that's our presentation. And now we're ready for questions.
So Ken, we have gotten a question from Twitter, and the question was, it's from Sawyer, and he asked if undersea volcanoes are still as hot as regular volcanoes.
Yeah, okay, that's an excellent question. And you know, the temperature of a volcano kind of reflects two different things. One of them is how hot is the magma, and how hot the magma is has a lot to do with what it's made of. And in fact, most of the volcanism that happens in the ocean has magma that's hotter than erupts on land. And this is partly why we have the oceans where we have them, because the type of rock that comes out of submarine volcanoes is not only hot, it's also very dense. And so when it piles up on the land, it makes depressions that then later have subsequently filled in with ocean. The other thing that determines how hot a particular volcano is at the surface is the nature of the eruption, how it happens, how magma cools as it's ascending. Does it start to interact with air or water on the way up, where it will start to transfer some heat? And for that aspect, we can see the full range of conditions in the submarine environment, as well as what we call the subaerial environment, volcanoes on land. You can see a range of temperatures at both settings. There's no sort of systematic difference between the oceans and on land. Most volcanoes, if you're seeing molten rock come out, it's very hot.
So another way to answer that question is what happens when there's to the hot spring water as it comes out of the seafloor. So when some of the seafloor hot springs can be like hotter than your oven in your kitchen can get. So really hot because of all the pressure of the ocean at the bottom of the ocean. It prevents the hot water from boiling, so it can get hotter and hotter and hotter. And but the amazing thing about hydrothermal vents is that the hot water is coming out like from a little nozzle in the seafloor, but it's coming out into this big cold ocean, and so it immediately mixes with the colder seawater. And so if you stick a thermometer right where the hot water is coming out, it can be like 500 or 600 degrees Fahrenheit. But if you just move that thermometer away just a little bit, it can be only like room temperature. And if you move it a little bit further, then it's almost just above freezing. So the temperature changes very quickly with distance away from where the hot springs are. So all the animals that live at the vents are adapted to different kind of temperature ranges that they want to be in. And so they don't want it too hot, but they don't want it too cold either. So that's another part of that question of how hot it is down there. Okay.
Thanks, Bill. Looks like we have a question from Mr. Janquart's class. Go ahead.
Go ahead.
So my question was, how many molten lava rocks have you collected, or when you tried to collect some, did it ever damage your vehicles?
So far, we've only been able to collect that one rock, and it took us many hours, lots of trial and error. So we're always cautious with the vehicles to not get them too close to the very, very hot material, or the material that's flying very quickly out of the volcano. But also, a lot of the vehicle is made out of special materials that can handle very high temperature. And that rod that we stuck in was made out of something called titanium. Any of you who are familiar with the Terminator, he's also made out of titanium. And so it could take the heat. And but it's something that we're always very cautious of. And we'd love to be able to collect another molten rock or several of them. But so far, we only have one.
But another kind of amazing thing about working at the bottom of the ocean compared to on land is, on land, if there was a volcanic vent, right in front of you, you would want to run the other way because it might explode and you wouldn't want to be there. But on the bottom of the ocean, again, because of all that pressure, it kind of subdues the explosive behavior, and as things are thrown out into the water, they slow down and fall closer to the vent. So with an ROV, you can get a lot closer to a vent, and even if it's erupting, than you could on land. So that's kind of gives us new views of how volcanoes work. Okay.
All right. Ms. Peluso, it looks like you guys have a question.
How long have you been doing this?
Let's see. I have been doing geology and working on volcanoes for about 25 years. I actually started working on land, so I worked at Mount St. Helens in Washington State for several years when I got out of college. And then I've worked in other places, Hawaii, the Galapagos, and then yeah, about 25 years ago, I started doing underwater volcanology and working in hydrothermal vents. How about you, Ken?
Yeah, my story's similar to Bill. About 25 years working at volcanoes. And I also like to work in volcanoes on land. One of my favorite places is Iceland. We like to compare the way the volcanoes look in different places and how they behave in different places, how eruptions happen in different settings, underwater, above water, all that stuff. Next question.
Okay, it looks like Mr. Peluso, you have another question.
Somebody here.
How do they erupt?
Well, so there's more than one way that a volcano erupts, and in general, when an eruption happens, there's some building up pressure beneath the ground from magma, which is hot, and it's rising up because it's got what we call buoyancy, and it's pushing on the rock around it, and then that rock cracks, it fails. And then something comes out of the ground, and that can be some combination of molten magma or broken up fragments. There's a lot of gas that comes out, and some eruptions will be very, very short, and some will last for a very long time. Many eruptions change what's happening during the eruption. They may start with a very rapid expulsion of magma and gas, and then things start to slow down, and magma continues to dribble out for a while. So there's a whole variety, and in fact, how a volcano erupts says a lot about what the volcano looks like. What kinds of material come out, the sizes of the pieces determine the shape of the volcano, and so it's a part of what we're interested in studying.
Okay, Mr. Jankwar, it looks like you guys have a question.
Are we gonna see the volcano erupt?
Yeah, that is an excellent question. And all we can say is we hope so. Yeah, we're all wondering this on this part of the expedition. What we're doing is making measurements in the water and looking for places that we think are likely to be experiencing an eruption. And then in a couple of weeks, when we have the remotely operated vehicle, Sebastian, we'll go to those places, and we all have our fingers crossed. If it isn't erupting, we still learn a lot of interesting things. But the fact that there have been so many recent eruptions here gives us, good confidence that at least in one or another spot, we're going to be seeing an eruption there. I'm being optimistic, maybe.
So Monica just read us a question from Twitter that was about can pressure waves from an eruption affect the ROV if it's diving nearby? And I would say no, because the ROV is, it's designed for working at the bottom of the ocean where there's lots of pressure already. And so it's like Ken was saying, a lot of it's made out of titanium, which is a very strong, light metal that doesn't corrode. So the ROV is designed for high pressure. And so even if the volcanic vent is having explosions, the ROV can take it. Thank goodness.
All right, let's try another question from Ms. Peluso.
How much lava comes out of a volcano?
How much lava comes out of a volcano? It depends. Eruptions can be of all sizes. They can be little tiny things where just a little bit comes out, or they can be really enormous things. It also depends on how long the eruption lasts. So there's a big range, and it kind of depends on how much magma is being supplied to the volcano from underneath. So if there's a big supply, if there's lots of magma coming up from the mantle up towards the surface, then the more there is, the more it wants to get out. The bigger the eruptions, the more frequent the eruptions. If the supply is really low, then just occasionally there's little blurps that come out. So these volcanoes we're working on are probably, well, this one that we've been highlighting called West Mata, it must have a pretty good supply because of all the eruptions it's had in the last 10 years. So it definitely has a higher supply than all the rest of them, which haven't had an eruption during that time period. So that's why we're particularly interested in this one where all the action has been, and we're hoping to see more.
Ms. Schwank, do you guys have a question? I think I see a hand raised in the background.
Yeah, let's see. Shinjini, why don't you come on up?
I have a question. When the lava comes up, usually water burns the fire out, and lava is almost like fire. So wouldn't the water burn the lava out?
That's a great question. So those pictures that Ken showed at the beginning where you saw the orange glow, yeah, it kind of looks like fire, but what it actually is rock that's melted. So it's so hot that it's like gooey. It's a liquid. So you're going from if you just had a rock in your hand, it's cold, right? So it's a solid thing. If you heated it up, it would turn into a liquid and melt. So that's what we call magma, which means molten rock. So when a volcano erupts, that's molten rock coming out, and the reason it's orange is because of its temperature. So the hotter it is, it goes from black when it's cold to red to orange to yellow to gets brighter and brighter. So it's the color is from the heat, and but you're right. All that ocean water is cold, and the water is trying to cool the surface of the lava. So as the lava's coming out, it's hot and molten, but almost immediately the surface is being cooled by the water. So it's not like putting out a fire, but it's definitely trying to cool it and solidify it. So if the faster the lava moves, the harder it is for the ocean water to cool it down, and that's why in some of those pictures you just saw cracks, glowing cracks, is because all the rest of the lava flow has already been cooled, and so it's dark, it's only glowing along the crack where that crust is split and the new magma is being exposed. It's a little hard to explain without seeing a video of it. So something you might do after this call is, Google pillow lava and see if you can find a video of pillow lava flowing, but you can kind of see that in motion. But that's a great question.
All right, Mr. Janquart, it looks like you guys have a question.
Can an underwater volcano become an island?
It can, yeah. If it has a big enough supply, if the volcano has a big enough supply of magma from below, then it starts as an underwater mountain and it keeps growing and growing. If there's enough supply, it can grow and grow until it gets near the ocean surface, and then it can grow above the ocean surface and become an island. Hawaii is a great example of that.
Yeah, Hawaii's where I live. And Hawaii does have a submarine volcano. We called it Lo'ihi. And it's still pretty far down. It's about 3,000 feet below the surface. And we don't expect it to poke up above the surface of the ocean for maybe another 10 or 20,000 years. But the other islands of Hawaii started out as submarine volcanoes that grew over a long time. Most of those volcanoes are active for more than 1 million years, and then they eventually reach the ocean surface. There are other kinds of submarine volcanoes that start relatively shallow and just in one eruption they can go from underwater to being above water. And a really good example of that is something called Surtsey. And Surtsey is off the south shore of Iceland. And we actually named the style of volcanism that happens when you have a shallow volcano that starts underwater and goes to above sea level, Surtsean. And there's some really great video on YouTube that happened back in the 60s, that eruption. It was filmed and very dramatic. There have been some more recent Surtsean style eruptions, including 2 of them here in the Kingdom of Tonga. Not where we're working, but farther south near the capital island called Nuku'alofa. There's been 2 Surtsean volcanic cones that have formed in the last decade. So it does happen. It's pretty frequent. There's another famous one that just occurred off of Japan in the last 5 years also. So it's pretty common. Question from Lucy, I guess on Twitter, where are most of the submarine volcanoes located? So, yeah, not sure if you're aware of how much of the details of, but the surface of the Earth is broken up into large blocks that we call plates. And these move around the surface of the Earth. They're both on land and under the ocean. And where plates come together, the boundaries between them is the most common place to find volcanoes, both under the sea and on land. There's really no difference in that regard. There are also some volcanoes that we find away from the edges of plates. We call those intraplate, places like Hawaii. But the very largest concentrations of volcanoes on the oceans are at the 2 types of plate boundaries where plates are spreading apart. We call those spreading centers. And then also places where plates come together, and we call those subduction zones.
Great. We have a question from Ms. Barajas.
How do volcanoes go under the sea?
So how do volcanoes go under the sea? Well, so volcanoes, whether it's on sea or on land, the stuff that forms a volcano starts forming very, very deep beneath the surface of the Earth, maybe something like 50 or 60 miles down. And down there in that part of the Earth, we call it the mantle, and it doesn't know if it's under the ocean or if it's on land. It doesn't know anything about what's happening on the surface of the Earth. For one or another reason, rock starts to melt. Solid mantle rock, it's solid, but it moves very slowly and starts to rise up towards the surface of the Earth. And as the pressure gets less, we call it decompression, it starts to melt. So then that molten magma finds its way up to the surface, and it only knows that it's under the ocean in the very, very last moment before it starts to erupt. And so these boundaries between the plates that I was just speaking of on the answer of the last question, they happen under the ocean and they happen on land. And so that's how we get volcanoes under the sea.
Let's get another question from Mr. Jancourt's class.
Is it dangerous when the volcano erupts by you?
Fortunately, not for us, because we're up on the ship at the ocean surface, and so if we're near an erupting volcano, it's about a mile underneath us, and so we can send an ROV down there to have a look, and again, the pressure of all the overlying ocean kind of keeps the eruptions from getting too big down there, and so we can observe what's happening. And fortunately, we're plenty safe up here on the surface because we're so far away.
All right, let's head back to Ms. Barajas' class.
How would the underwater volcanoes form?
Well, let's see. They kind of depends what area you're in. In some areas, there's mostly lava flows that come out, and so a volcano would form by just piling up of lava flows. In other places, they're more explosive, and so every explosion would pile up lots of ash and rocks and debris, and so that would form a steeper kind of volcano. So basically, the magma that comes out of the ground at a volcano builds up the volcano itself. A volcano is really just a pile of stuff that's come out of the earth. So, some have more lava flows and they're more solid, and some are more just like a pile of ash and broken up rock.
Let's try another question from Miss Schwenk.
Is there any fishes that live by the volcano?
Okay, I don't know.
There are in the deep ocean. There are some fish that live everywhere and kind of cruise around and look for things that have fallen down from the surface to eat. So we see, but there's not very many of them. So we see when we make dives to the seafloor, we see them swimming around. At hydrothermal vents, though, these seafloor hot springs where there's all the animals around that get energy from the chemicals coming out in the hot spring fluid, there's a lot more animals there, and there's certain fishes that only live at hydrothermal vents. So we see them sometimes also. So so there's kind of the background fishes that don't depend on the hot springs, and then there's some fishes that only live at the hot springs. So there's both kinds. We also see octopus, depending on we showed some pictures of various kinds of vent animals. There's snails and crabs and mussels and clams and things called tube worms. There's lots of different kind of worms that live at the hydrothermal vents. Octopus are always fun to see, though.
We'll ask a question from Miss Peluso's class, and then a question from Mr. Jancourt's class. So Miss Peluso's class, go ahead.
What kind of things do you have to wear when you go underwater?
Well, actually, we don't have to go underwater at all, because when we're doing this work, we're staying on the ship, and we send these robotic vehicles down, and so there's no people inside those things. They're just a machine. So the AUV sentry goes down and swims by itself, and we can talk to it with sound. We can send messages back and forth. And the ROV that goes down on a cable, again, it's just a robotic vehicle, and we control it from up here on the ship. So because we're working in such deep water, it's deeper than scuba divers can go, so like way deeper. So that's why we use these machines instead of jumping in the water and swimming around in a scuba suit.
All right, let's go to Mr. Jancourt's class now.
How many areas and what areas have you been to discovering volcanoes?
Let's see. Well, so we're in this area between Samoa and Fiji, north of New Zealand. Ken and I both worked down here before. Other places I've worked include the Mariana area, so that's north of Guam and south of Japan in the Western Pacific. I've done a lot of work offshore Oregon and Washington. In the Northeast Pacific. Those are the main places I've worked. How about you, Ken?
So in the oceans, some of those same places that Bill mentioned, I also do work on a thing called the East Pacific Rise, and that runs continuously off the coast from Mexico all the way down to the tip of South America. I've worked off of Mexico, off of Costa Rica, off of Chile near Easter Island. And there's another spreading center that crosses it near the Galapagos Islands, and I've worked there quite a bit. And each one of these places is a little bit different. It's always fun to do these studies in different places, not only because the volcanoes are different, but also the ship starts out in a different location, and you get to see something about the culture and the place that you're traveling from, which is also really fun.
Like this trip started in Samoa, so we all flew here by airplane to Samoa and spent a few days and got to see a little bit of Samoa before we got on the ship and left port.
Thank you. Let's get a question from Ms. Barajas and then Ms. Schwenk after that. Ms. Barajas?
What? Since magma comes from the center of the earth, how does it go up the surface like the volcano?
So how does magma get from deep in the earth to the surface?
Yeah.
Many times it comes up by forming a crack and then flowing through that crack. Because the magma that's underground, if it's accumulating, it's building up pressure in some sort of reservoir or something. It's kind of like a balloon inflating, and if that when that pressure gets too high, then what happens is a crack opens up in the roof, and then the magma flows through the crack up to the surface. Once at some volcanoes, it's more like a pipe that goes up. Like once it's erupted a lot of times, it can sort of change from a crack to a pipe, and then the magma can go up the pipe that way. So kind of depends. If it's been a long time since it erupted, then it's more likely to come up through a crack, or if it's been erupting for a long time, then it could be more like a pipe.
Okay, Ms. Peluso, looks like you guys have a question.
Did lava start off from a solid into a liquid?
Yeah, it did. That's a great insight. So usually before we make magma, there's solid rock, and that solid rock starts to melt because it's hot, and usually contributing to that is it's being lowered in pressure because it's rising up. Hot things tend to rise, and so even hot rock, it very, very slowly creeps around in the interior of Earth. In the mantle, it's a little bit mushy there, and so the rock can deform and rise up, and it starts to melt. And pretty much every lava that erupts on the surface is only what we call a partial melt of the rock that's underneath it. So the rock that it came from only melts a little bit. It would be like if you took an ice cube and you set it out on the sidewalk on a hot day for just a minute, and part of it melts and part of it doesn't. And it turns out that when you don't melt something completely, the melt is a little bit different than the solid it came from. And so the magma that makes lava forms in that way. And depending on how much the rock melts, a little bit or a lot, says a lot to do with how the magma chemistry is going to be, because some things like the gases that make magmas erupt really explosively, as soon as a rock starts to melt, they like to go into the magma. Some of the other parts that make up the magma, the chemical components, they're kind of reluctant to enter the magma. And so it changes how runny the magma is, how hot the magma is, how gassy it is. But in general, that's the process. It starts out as a solid and it melts a little.
Okay, cool. I didn't know all that. That's pretty neat. It sounds like Ms. Schwenke, you guys have a question.
Okay, Emily. How many volcanoes have you located or seen so far?
Yeah, that's a great question. So in this area, that we're working in right now, there's about 30 volcanoes in an area that's about 30 miles by 30 miles, kind of roughly square. There's volcanoes all over the place. Some of them are not active, and some of them are older than others. And so the bigger the area we look, the more volcanoes we'll see. But in this area, there's 9 of them that we're really focused on. They're in a group together. We call them the Meta Volcanoes, and we're really interested in those. And then there's a couple of volcanoes to the south, including one very big one, which we didn't show you a picture of. It's called Nagoya Tahi. And that one's another very interesting volcano. There's in the past, we've been in this area and we've studied volcanoes in sort of neighboring areas. But because we want to learn a lot, we've decided to restrict ourselves to just a handful of these volcanoes. We picked the ones that we thought would be the most interesting, and those are the ones we're focusing on now. But the bigger the box you draw on the seafloor in this area, the more volcanoes you would see. And there's literally hundreds of them in the Kingdom of Tonga, just that one little country.
Cool. That's cool. So it looks like you guys have a question.
How hot is the lava in the volcano?
How hot is the lava? Yeah, so the temperatures of the lavas depend on lots of different things. They can be, so as scientists, we usually use the metric system for temperature. So we use something called centigrade. And so the hottest magmas that we know that, or Celsius is another term that means the same thing, that we see erupting on Earth today are about 1,400 degrees C. In the past, Earth was much hotter in its earlier days, and so several billion years ago, we saw magmas erupting at the surface that were about 1,600 degrees, and we weren't there to measure them directly, but we use the science of thermodynamics, which allows us to compare the minerals that are present and the temperatures that we know that they form at to sort of back out the temperatures. If you want to convert between, in a very rough way, between centigrade or Celsius and Fahrenheit, you can basically just double the temperature in Fahrenheit. And it's not exactly right, but it's close enough. So something that's 1,400 degrees, would be something like 2,500 or so degrees. It's very hot, very, very hot. Those are the hottest ones. The coolest magmas that we see erupting on Earth, there's some relatively cool ones. They're maybe only 700 degrees centigrade, or something like 1,300 degrees Fahrenheit. But again, still way too hot to touch.
All right, let's see if Miss Bras has a question for us.
How is magma formed?
How is magma formed? Let's see. We talked about Ken talked about some of this when he was talking about solid rock in the mantle that rises and melts a little bit. So that's the main way. The reason why most volcanoes are at plate boundaries is because where two plates are spreading apart, that motion of the plates makes the mantle well up where the plates are spreading apart. So that kind of adds to the mantle rocks rising towards the surface and melting. Where plates are running into each other and one gets forced underneath the other, that also leads to the one that's going down usually causes melting above it, and then that magma makes its way to the surface. So that's why volcanoes and most of the planet's earthquakes also are at these plate boundaries, because both the earthquakes and the volcanoes are sort of consequences of the plates either spreading or running into each other.
All right, Mr. Jankwart, do you guys have a question? Okay, we can come back to you. It like Ms. Schwank has a question. Would you like to ask a question?
In the future, do you hope to have titanium suits or something that you can go down and see them for yourself?
That would be fun. That would be fun. I want one. Well, there are kind of dive suits that people can go in, and where you can go deeper than you can scuba dive. But even those can only go down, I don't know how far. Do you know, Ken? Probably 100 meters or 300 feet or so. So like scuba divers can go to about 100 feet. So these suits that are, people get in and they look like a robot with a with a windshield or something. Yeah, they can maybe go down to 300 feet or maybe a little more. And then beyond that, for people to go deeper, they have to be in a submarine. So, the Navy has big submarines. Scientists have little tiny submarines. Both Ken and I have been in a submarine called Alvin, and it takes 3 people. So, and the people get in this this ball that's made out of titanium, because that's again a really strong light metal that doesn't corrode, so it's good for working in the bottom of the ocean. And so the 3 people get inside the ball, and the ball is encased in a bigger submarine, and it's got arms and stuff. So it's the whole thing's about the size of a UPS truck or something like that. So the Alvin can go down to I guess not that much, 4,500 meters. So that's something like 14,000 feet or something like that. So that's pretty far. So the people are inside the submarine, so not outside. And the ROVs we use can go down to about the same depth, but in that case, we all get to stay up on the ship, and when you go in the Alvin is battery powered, so each dive is about 8 hours long. So you get in the Alvin on the ship, then they lift Alvin and put it in the water, and then it sinks down to the bottom. It takes about an hour to get down there. And then you drive around, do your work on the bottom, and then at the end you drop some weights, and the Alvin floats back up to the surface, and it picks it up and puts it back on the ship. So whatever method you use to work in the ocean depends on where you are, what depth you want to go to, and we're working really deep, so we have to use these the things like ROVs.
So I just wanted to add to that answer one thing, which is that as scientists, I think one of the things that is so interesting for us studying volcanoes is being able to see what's happening there. And part of that is going there. So if I had my choice, I would always try to go to the volcano personally. But we have various kinds of trade-offs in our science. And one of the benefits of using robotic technology is that many more people get to visit the volcano. They don't get to go there in person, but they get to see in real time while the vehicle is there. And we can talk with each other and interact. If we were all in individual suits, we might not be able to converse with each other and describe what we're seeing and make plans for what we're doing. And so something that Schmidt Ocean Institute, who is the sponsor of this research expedition, likes to do is they're trying to develop new technologies, especially robotic technologies and remote technologies that can bring these amazing views of things like volcanoes to more and more people. And one of the things that we're able to do with the remotely operated vehicle that you'll see in a couple of weeks if you follow us is you can be there with us watching in real time on the cameras, on YouTube or on Facebook, seeing the eruptions. And so there's kind of a trade-off between going there in person and only a few people get to see it, or having as many people as possible see it. And that's part of what we're doing on this expedition, is going there and bringing it to you all at the same time as we're seeing it.
Okay, cool. We're running close on time, so we're going to do 2 more questions. The first from Mr. Janquart, and then the second from Ms. Peluso. So go ahead, Mr.
Go ahead.
When a volcano erupts, do bubbles come out of the top, like white stuff? Because in one of the pictures I saw, when a volcano erupts, it had like a lava on it, and then white stuff was coming out of it.
Yeah, so lots of different things can come out of the top of the volcano, and what form they take depends sort of on how deep they are. So that white stuff that you were seeing it looks like smoke, and you know, smoke when it's happening in the air is just very, very fine particles that are mixed with warm air, and that's what makes them rise up. And in that sense, that you're seeing the same thing under the water. The particles are little bits of sulfur, and they look a little bit like smoke in the water, and the water is heated up, and so they sort of move up in that sense. And that sulfur was a gas that condensed directly into making a little particle. There are other gases like carbon dioxide, which release from the magma just the same way that carbon dioxide, if you open up a can of soda and you pour it into a cup and you see those little bubbles coming out. And it turns out that the carbon dioxide will make bubbles if we're shallower than a certain depth in the ocean. And if we get deeper than that depth, then when the carbon dioxide comes out of the magma, it doesn't make a bubble. If there's enough of it there, it will make a little droplet of liquid. And you would think, well, how do you get a droplet of liquid under the water? But you can see them moving around, and eventually as they migrate up into the water, they will turn into gas, or if they're small enough, they will dissolve into the ocean water. And some of the volcanoes Bill has worked at have been a little bit more shallow, and so they've seen these bubbles of carbon dioxide coming out of the seafloor. We don't really see that in this area. There's one volcano not too far from here. We're not going to study it on this expedition, called Niua, where we have seen those carbon dioxide bubbles come out. But because the volcanoes we're working on here are pretty deep, instead the gases, instead of making bubbles, when they come out of the magma, they immediately turn into solid particles. They condense or they dissolve into the water, and we don't really see a trace of the gas bubbles anymore.
Well, that's really neat. So our last question is now for Miss Peluso. Please go ahead.
What are the volcanoes you've discovered?
So the volcano, oh yeah, sorry.
What are the volcanoes you discovered?
You're asking what are they? Like, what are their names?
Yeah.
Yep. So some of the volcanoes that we've discovered, we've given names to, but since the place that we're in is a country, and the country is mostly little islands, and there's a king, and the king has the responsibility of naming the places in his country, and so some of them he has given names to, some of them we've given names, and then he has approved those names. So some of the names, we call these volcanoes Mata, which means eye in Tongan, because when you look at them on a map, they look a little bit like an eye. So we have a west and an east Mata, and then we have 7 other volcanoes. I'll say their names for you. Mata Ua, Mata Taha, Mata Tolu, Mata Fa, Mata Nima, Mata Ono, and Mata Fitu. And those are just the numbers, 1 through 7 in Tongan, but they sound pretty cool when you say them out. We have volcanoes. We have a Nagoya Tahi. We have one called Niua. There's a Tonga Tapu Tapu. There's one called Mangatolo. And then on top of those, we have a whole bunch that we haven't really given formal names to, but when we're talking about them informally, we we have to call them something. So we have one that we call Boko, and Boko stands for Bob's Cone, and that would never go on a map, but it was. We have a colleague. He's not with us this time, but he usually comes to sea with us, named Bob, and he was looking at the map one day. He goes, "Oh, this place looks pretty interesting," and we've gone there, and it is interesting. So now we talk about it. And we call it Bob's Cone. We have other places that we did informally name things like Swelko and Nelskrijk, and it's always a little bit fun. But when it comes to like officially giving something a name, we like to try and use the name of the place. And here we are in Tonga, so we like to use Tongan names. And of course, if the king decides he doesn't like the name, or he wants to change the name, that's his right. He's the king. So, for instance, in the olden days, we used to call Nagoya Tahi Volcano O, and that's because someone else came to this place before us and named some of the volcanoes just with the letters of the alphabet, and then it later got changed to Nagoya Tahi, and I like that name better.
Cool, thank you very much. Well, I'm afraid, I know we have more questions, but I'm afraid we've run out of time. So one of the nice things about how we're doing stuff is we are connected to the ship on the internet. So if you do have questions that we didn't get to, please continue to let us know. You can let us know over Twitter or Facebook or even Instagram. All of our handles are at schmidtocean.org. Our website is www.schmidtocean.org. On there, you can also email us these questions. So thank you again to everyone for showing up. Thank you very much for all the great questions. Thank you to the scientists and the ship for making time for this. And hopefully we will see you around online on social media. Thanks, everyone.
Bye.